So today we want to continue with the solution of linear second order differential equation using the operator method. We had done up to example 5. Now we are going to example 6. So example 6. Solve the DE. Solve the d squared x dt squared plus 9x is equal to 4 cos 3t using the operator method. The operator method. Using the operator method. So in our solution, we say x will be equal to xe plus xp. This implies what? D squared plus 9 into xc gives us a 0. The auxiliary quadratic equation now will be m squared plus 9 is equals to 0. Is equals to 0. So this gives us m will be equal to plus or minus j3. Plus or minus, which is equal to 0 plus minus j3, which resembles alpha plus or minus j beta. So beta is there, alpha is there. So we say our xc will be equal to what? Just a cos 3t plus b sin 3t. Because e power 0t, e power 0 is 1. So 1 multiplying the whole of this, that's what we are getting. So that is our complementary function that we have gotten for this particular differential equation. Now we move to a solution of the particular integral. We say, but we know d squared plus 9 into xp. This is the one to bring 4 cos 3t. 4 cos 3t. So our xp will be equal to 1 all over d squared plus 9 multiplying 4 cos 3t, which will be equal to, this 4 will come outside here, and that 4 will pass the operator, so it is a constant, d squared plus 9. This one multiplying cos 3t, which will be equal to 4. If we apply theorem 3, our a here is 3. You square it, you get 9. Give it a negative sign so that you substitute where there is d squared. It will be 1 all over negative 9 plus 9, which now we multiply with cos 3t. And this one cannot happen. There is a question mark because 1 over 0 is undefined. It gives us an infinite value. So this one cannot occur. So we say theorem 3 has failed. Theorem 3 has failed. If theorem 3 has failed, we now check on another way of writing cos 3t. Now this will be equal to 4, and then we go back to where we came from. 1 all over d squared plus 9. And from Euler's formula, cos 3t can be a real part of exponential j3t from Euler's formula. It can be real part of that. So a real, and whatever we have here is a real, the final answer will just be a real value. So we say this word real, we can take it out. Then we remain with now 4 into 1 all over d squared plus 9. Now multiplying exponential j3t. Which will be equal to a real part. Then we have here 4, 1 all over d squared plus 9. Now, this is a pure exponential term. And now, if we apply Theorem 1 for pure exponential terms, then Theorem 1 will also fail. So since j3 will be our a, when you square j3 you get negative 9. Negative 9 plus 9, Theorem 1 will also fail. So we simply move to application of Theorem 2. So this one multiplies 1. This one multiplies 1. Which will be equal to real part of 4. Then this exponential will pass. It will pass the function of d. And where there was d, now we put d plus a. So we put d plus a, so it will be d. Our a is j3. Then we square that. Then we add 9. The whole of this will now act on 1. Will now act on 1, which will be equal to real part of 4 exponential j3t into now 1. If we expand this, what we get is d squared plus 6 j6d j6d plus, not plus, we have here minus 9, then now plus this other 9. This one now acting on 1, acting on 1, which will be equal to real part of 4 exponential j3t. And we remain with 1 all over d squared plus j6d. But 1 has got so many names on this earth. 1 can be called e power 0t, t power 0. It can also be called cos 0t. So we use cos 0t here so that we shorten the working. Cos 0t is also 1. This will be equal to real part of 4 exponential j3t. Applying Theorem 3, because we have a cosine now, our a is now 0. When you square 0, you get 0. You get negative 1 times 0 is also 0. And we replace where there was d squared. So this one will be now 1 all over 0 plus j6d. The whole of this multiplying cos 0t, cos 0t. We close. From there we say this is the same as real part of 4 exponential j 3t. Now this one we have 1 all over j6 multiplying 1 all over d. Cos 0t is the same as just 1 again. So we convert it back to its original name, which is what? 1. So this will be equal to real part of 4 divided by j6 we get, that is 4 all over j6. We have exponential j3t. 1 over d, it is the integral of 1 with respect to the polynomial concerned, with respect to t. We were working on a function of t. So this will be real part of. This is 2 all over 3. 2 all over 3. Then we have here 1 all over j. Then we have here exponential j3t. The integral of 1 with respect to t is just t. We close. Which will be equal to real part of 2 all over 3. We have t here. 1 all over j is the same as minus j. That is, when you multiply both the numerator and the denominator by the conjugate of the denominator, the conjugate of this will be minus j. 1 times minus j is minus j. The j times minus j is 1. So negative j all over 1 is just negative j. Exponential j3t in full is from Euler's formula is cos 3t plus j sine 3t. That is the exponential j3t. This t we have included, so we close our bracket. This one will be equal to real part of. And now we want to multiply. We have 2 all over 3t. Minus j times this, we get minus j cos 3t. Minus j times plus j, you get 1. So we say plus sine 3t. So from here, we say the real part of what we have in this bracket will be 2 all over 3 t sine 3t. And that becomes our xp. So we've gotten that value by use of the operator theorems or the operator method. So that is our xp. From there now we can now write. We can now write the general solution of our differential equation. So general solution GS, x will be equal to now, we know it is xe plus xp, which will be equal to a cos 3t plus b sine 3t plus 2 all over 3. 2 all over 3 t sine 3t. 2 all over 3 t sine 3t. And that is now the solution to that differential equation. So, example 7. So solve the d squared y dx squared plus dy dx is equal to x e power minus x. Given that when x is 0, y is equals to 2, and dy dx is equal to 0. But use the operator method. Use the operator method. So in our solution, y will be equal to yc plus yp. So this implies what? A d squared plus d all into yc should give us 0. The auxiliary quadratic equation will be what now? That will be m squared plus m is equals to 0. So this is m into m plus 1 is equals to 0. M is equal to 0 or m is equals to negative 1. This implies what? Our yc will be equal to a plus be power negative x plus be power negative x. So we can now proceed with the solution of the particular integral where we are going to inject the d operator theorems. So we have, but we know d squared plus d, this one multiplying yp, it is the one to generate x e power minus x. So if that is the case here now, we say yp will be equal to 1 all over d squared plus d acting on x exponential negative x, which will be equal to 1 all over. We can factorize one of the d's out. This is the same as 1 all over d multiplying 1 all over d plus 1. Now acting on x e power minus x, which we can write as 1 all over d. Now multiplying 1 all over 1 plus d. 1 all over 1 plus d squared, yeah. So this is acting on x e power minus x. Now we have an exponential multiplying another function of x. So here we are going to use theorem 2 of our d operator theorems. So this will be equal to 1 all over d. The exponential will pass. The exponential will pass. And when our exponential passes, we have this one. Where there was a d, we input this a negative. Where our a here is a negative. Where there was a d now, we put d plus a. So it will be 1 plus, well, there was this d, we put d plus a. And our d and our a is negative 1, so minus 1. So d minus 1 has replaced the d, according to theorem number what? Number 2. Now we let this one act on x, which will be equal to 1 all over d multiplying the exponential, multiplying 1 all over d, now acting on what? On x, which gives us what? 1 all over d to multiply e power minus x, but 1 over d multiplying x, that is we are integrating x. So we get x squared all over what? All over 2. Which will be equal to, now x squared all over 2, a half is a constant, it can move out. So it passes the operator. So we have 1 all over d, now multiplying x squared e power minus what? Minus x. 1 over d multiplying x squared e power minus x. From here we can also use theorem 2, because this is a function of x. Now multiplying an exponential, we can use theorem 2. So this will be equal to a half. This equals to a half. Then this one passes, exponential minus x. Then where there was a d, we insert d plus a. So d plus negative 1. So d minus 1. And now this one is multiplying what? X squared, which is equals to a half exponential negative x. This one can be written as 1 or negative 1 all over 1 minus d. Multiplying a negative, you multiply numerator and denominator by negative 1. So this is negative 1, this becomes a minus, this becomes a plus. We are doing so that we can be able to apply the binomial theorem, since what is remaining is a pure polynomial. Which is equals to a half. Negative comes out, negative a half exponential negative x into now 1 minus d, which has been raised to power minus 1, multiplying x squared, which is negative a half exponential negative x. We have this as, when we expand, we get 1 plus d squared plus d cubed plus others. This one multiplying what? X squared, which is equals to negative a half e power minus x into 1 times x squared is x squared. D times x squared is 2x. D squared times x squared is 2. Therefore, our yp will be equal to negative a half exponential negative x into x squared plus 2x plus 2. And that is the particular integral. From there, let's write down the general solution. General solution. So the general solution, y will be equal to yc plus yp. yc plus yp. Which will be equal to, our yc was a plus b e power minus what? X. Now we have yc is minus a half exponential negative x into x squared plus 2x plus 2 plus 2. So y is equal to yc plus yp, we have that. But there were conditions given, so we need a dy d what? Dx. A dy dx will now be minus b exponential negative x. We are differentiating this to get our dy dx. So we say we have minus a half exponential negative x into 2x plus 2. We are differentiating. Plus a half. We are now, first we differentiated what is inside the bracket. Now we are keeping what is inside the bracket constant and we differentiate what is outside here. That's the exponential negative x, which gives us now negative comes forward to meet a negative. It is a half positive, then exponential negative x into x squared plus 2x plus 2. That's what we are having. That's what we are having. So we say when x is equals to 0, y is equals to 2. So when x is equal to 0, y is equals to 2. So where there is y, we put 2. Where there is y, we put 2 here. That's why 2 is equals to a. X is 0, a plus b. E power 0 is 1. A power 0 is, that is now minus a half. X is 0 into 0, 0, then 2. 0, 0, then 2. So 2 is equals to a plus b minus 1. Therefore, a plus b is equals to 3. A plus b is equal to 3 when x is equals to 0. dy dx is equals to also 0. So we say 0, we substitute here, 0 is equals to minus b. Minus b. Then we have minus a half into 2. Then we have plus a half into 2. Plus a half into 2. Because this one 0, 0, that is this one here, minus a half into 2. So we can see here 0 is equals to minus b. So b is equal to 0. B is equal to 0. Because this one will cancel that. Therefore, particular solution, y will be equal to now, b is equal to 0, and b is equal to 0, and if our b is 0, our a is equal to 3. This implies our a is equals to what? 3. So particular solution, y is equals to 3 minus a half exponential negative x into x squared plus 2x plus 2. And that is the solution to that differential equation. That is the solution to that differential equation. So we are through now with the d operator method. What remains now is maybe on our second order or on our differential equation. What remains now is the application of differential equations.